Hello everyone, welcome to Recitation Week 3 for CEE222 Water Resources Engineering. As always, today we will have 6 different questions, and the first question will be 4.2.3 in your textbook. So let me get started with the question. Okay, let's first read the question. Here we have a siphon with a cross-section area of 12 square feet, as you can see here, and it is used to discharge water to a downstream reservoir, which is here below its summit. So the downstream is 60 feet below this summit, and also upstream water surface level is 8 feet below this summit. So here we have 8 feet from the summit to the surface of this reservoir. And in this question, we need to determine the danger of cavitation. So the danger of cavitation occurs when the pressure is lower than minus 9.8 per over square inch. So that we actually need to find the pressure at the summit because the cavitation is most likely occur at this point, so that we need to find pressure here, and to find the pressure we also need to find velocity inside this pipe. And also in the question we have additional information. So it says that the friction head loss throughout this pipe is equal to 2.5 times velocity head. So here we have friction head loss, which is this term. And also it says that the distance from the siphon entrance to the summit, so from entrance to the summit, is 1/5 the total siphon length. So if we say this length as k, the remaining will be 4k. Since the entire head loss throughout this pipe is 2.5 velocity head, the friction head loss for this part will be 0.5 v square over 2g. Also, even it's not given in the question, we know that we have minor losses. So here we have a minor loss at the entrance to the pipe. So the loss coefficient for this loss is 0.5. And when we are leaving the pipe, we will have another loss. So it will be KD, and KD is given as 1, and the KE is 0.5. So we will be using these values to calculate total head loss. Okay, since we need to find the velocity and pressure here, we need to write energy equation between these two reservoirs, because it will give the velocity in this pipe, and finally we can calculate the pressure. So let me write the first side of the energy equation, which is pressure at point A, velocity head for point A, and the elevation of this point. And if we skip to the here, we will have another pressure term, pressure head. We have velocity head for this point B. We have the elevation, and finally we have head loss, because the water is moving from point A, or from this reservoir, to point B, so that throughout this pipe we will have some losses, as I mentioned. So basically we have two different losses. The first one is HF, and the other one is minor loss, and let me say H minor. And for this minor loss, as I mentioned, we have entrance to pipe and leaving the pipe losses, and other minor losses are neglected for this question. So let me simplify this energy equation because we will have some zero values here. The first one will be the pressure at this point because it is open to atmosphere, so the pressure will be assumed as zero. And additionally, we will have the same situation for point B because it is also open to atmosphere, so the pressure is zero. Another term that we will be removing is velocity. Since these are very large tanks or reservoirs, there will be a little movement only at the surface, so that we can assume that there is no flow or velocity at all. So this term and this term is also zero at this point and at this point. Okay, the remaining is we have HA, which is the elevation of this point, and HB and head losses. So if we take this point as reference, so let's say this is point 0 at 0 feet. The point here will be 52 because the total distance from summit to this downstream reservoir is 60 feet, and the upstream of the highest point, sorry, the upstream of this reservoir is 8 feet below the summit, so it will be 52. And then we can continue with the question. So 52 feet is equal to total head loss. So for frictional head loss, as you calculated, we had 2.5 times velocity head. So it will be 2.5 v square over 2g, and this is head loss for the entire pipe. And additionally, we will have minor losses. So we have two minor losses here because others are neglected, so that it will be 0.5 plus 1 v square over 2g. So from that we will have 52 feet is equal to 2.5 plus 0.5 plus 1. So it is 4 v square over 2g, which gives us the velocity head, or v square over 2g, is 13 feet. So this is an important part or important step of this question, because we know the velocity head right now, and we can get velocity using this value. So the most important thing to find here is the pressure at this point, so that we can actually write an energy equation between point A and point S. Because we don't need other remaining parts, we will need only these pipes values. So let me write the energy equation again. It is from A to S. And this time it will be PS Vs square over 2g Hs plus total head loss. So now we can simplify same things here. So the pressure and the velocity will be 0 again, because we are still talking about the point A here. And we have HA, this time we can take this as reference, so it will be 0. And on this side, of course, we will have pressure, of course we will have velocity, and the elevation is 8 feet because it is given in the question. So this distance is 8 feet here, and we will have head loss. Similar to this equation, we will have two different head loss terms, which is HF and HM. For HF this time, since we will get this length, so which is the only K, so the head loss, the friction head loss was 0.5 here. And we will have minor loss, which will be only this one because we are not considering this part, so it is also 0.5 v square over 2g. Okay, so let me simplify this question again. Eight feet plus PS over gamma plus VS square over gamma plus the head loss, which is 0.5 plus 0.5 V square over 2g. So from that we can get minus 0 is equal, from that we have 2v square over 2g. So Vs is equal to v because the velocity is same throughout the pipe, so that they will be equal, so that we have 2 v square over 2g, and 1 v square over 2g was 13 feet, so in total we will have 20 feet plus 8, which is coming from the elevation difference, plus PS over gamma. Okay, let me continue from here because I was out of space. So from here we have 34 feet is equal to pressure at point S over gamma. So we need to directly find the pressure, and the specific weight of water is 62 pound per cubic feet. So from here PS will be equal to 62 times pound per cubic feet times minus 34 feet, and since we need to find this in inch and this is feet, we will also divide it by 144, and from here we can get minus 14 point minus 14.7 pound per square inch, and obviously it is lower than this value. So we can say that the system is in the danger of cavitation. So danger of cavitation.
Okay, let's continue with the second question. Here we have a pump that we will be using to remove 50 cubic feet per second flow rate of groundwater from an aquifer. And the diameter of the pipe is 24 inch. And we have an entrance screen, which is the loss coefficient as 2.5. And we need to find the maximum height above the aquifer that the pump can be placed without encountering cavitation. And we are assuming that the friction losses on the suction side of the pump are negligible. So as we always do, we can write an energy equation between point A and point S. And of course, we are going to remove some values here. First of all, we don't have velocity at the surface. And since it is open to atmosphere, we will have zero pressure. And also, if we take this point A as reference, we will have 0 feet here. And of course, we need to find HS here. In the question, we are going to find the velocity. So the velocity at suction head will be equal to velocity of the system, which is equal to Q over A, and it is equal 50 cubic feet per second. P times, and it gives 15 feet per second. So we have this velocity here, so we can directly calculate HS. Sorry. Gravitational acceleration, 32.17. And now we will have PS over gamma. And if you check your textbook, there's a paragraph before example 4.4. And it says that we shouldn't exceed a pressure head of minus 23 feet to prevent cavitation. So we will take this value directly. So we will have 23 feet plus head losses. And for the head loss, we will have V square over 2G. And we only have 2.5 because the frictional loss and other minor losses are neglected. We only have entrance, which is here. So basically, HS plus velocity head minus 23 plus 15.9 square over 2G times 2.5 is equal to 0. And from here, we can get HS as 9.26 feet. So this is the value of this point. the point of the pump so that we can prevent cavitation.
Okay, let's continue with next question, which is 4.2.9. So in this question, we have a system with a pump, and this pump is used to lift water from reservoir A to B. The length of the pipeline is 100 meters. The pipe is rough concrete with a 80 centimeters, and the roughness value is 0.6 millimeters. And the kinematic viscosity we are going to use is 1.10 to the power of minus 6. And this system is designed to carry water with a flow rate of 4.5 cubic meter per second. So in this question, we need to determine the maximum distance from reservoir A to pump so that the pump could be installed without encountering cavitation problem. Since we need to find the point between this reservoir A and pump, we are going to write energy equation between these points so that we can define a point, which is point S here, which represents the suction side of this pump. So let me write the energy equation between point A and S. As always, the pressure at point A and the elevation of point A. And now pressure at S, the velocity, the elevation, and finally, of course, the head loss, because water will be moving from this point to this point. So there will be some losses like minor loss and friction losses. So we can actually remove some values here, as we always do. So the pressure at point A is 0 because it is open to atmosphere, so it is 0. Similar to first question, the velocity will be 0 at this point because it is very large and there is a little movement. And we have this elevation. So from the surface of this reservoir to this point, which is the suction side of this pump, is 4 meters. So let me write 4 meters. And on the other hand, we cannot eliminate these values because there will be pressure and there will be velocity at this point. But we can take this point, which is S, as 0 feet as reference. So it will be 0. So let me continue with the question. So eventually we will have 4 meter is equal PS over gamma plus velocity head and the total head loss. For the total head loss, we will have frictional loss, which is HF, and the minor loss, which is HM. For the minor loss, we only have this one, which is entrance to pipe. So we are going to use KE at this point, and it is 0.5. And also we will have a frictional loss, but before that I want to write entire head loss term. Which is HF plus 0.5 V square over 2G. So here we have velocity, and we can actually find that because we already know the flow rate here. So V is equal to Q over A from continuity equation. Q is 4.5 and area is P d square over 4. So we can write P this is in meters, not centimeter, of course. And from here we can get velocity as 8.95 meter per second. So here we have this value, but unfortunately we cannot calculate the friction loss here because it has F and V square over 2GD. And when we look at here, we know this term, we know this one, we know this one, but we will need to find friction factor, which is F. So as always, we are going to use Moody diagram. And to check the friction factor from Moody diagram, we need two terms. The first one is Reynolds number, and the second one is E over D, which is the roughness over diameter. And for the Reynolds number, we have diameter times velocity over kinematic viscosity, which is 0.8 times 8.95 over the kinematic viscosity, which gives 7.16 times 10 to the power of 6. And for ED, we will have 0.6 millimeter over 800 millimeter, and it gives 0.0075. Since we did many examples with the Moody diagram, I will directly write the friction factor based on these two values. So from here, the friction factor is 0.0185. Okay, and also from your textbook you will find information. So the information says that negative pressure should not be allowed to exceed approximately 2/3 of standard atmospheric pressure head, or it shouldn't exceed 8 meters for the cavitation. So the maximum value can be -8 meters to prevent cavitation. And let me write that. This is allowable water pressure head. So this means that PS over gamma, which is pressure head at this point, should be minus 7 meters. So knowing that and knowing this equation, we can merge two of these equations, and using the friction factor and other terms, we can calculate the maximum length that we can use here. So let me write from equation 1 4 meters is going to be equal to minus 7, which is this term. Actually, let me write that. Plus, we will have v square over 3g here. We will have another v square over 2g, and we will have another one, so that I can write it in parentheses as like this one. So we have 1 here. We have 1 here, we have 0.5 here, plus we have this friction loss, so we have F, which is 0.0185 times the length, which is we will be finding. So let me write L over, we have 2 times 9.81, which is the gravitational acceleration, and the d is 0.8, and we are closing parentheses. So now we have everything to find the value here, which is maximum length from point A to suction side of the pipe. And we also know the velocity here, which was 8.95 meter per second. So from here, LP will be 51.6 meters. If it is not visible, I will write it here. So clearly, the maximum length we can use is 51.6 meters, which will be the value from reservoir A to the suction side of pump. So if we do that, we can prevent cavitation. And the tricky part was here using -7 meter for the pressure head at this point. And you can check your textbook, and you will find the text before example 4.4. So let me write it here. Once we write this value in this equation 1, which is the energy equation between point A and point S, and also after finding the friction factor from Moody diagram, we can calculate the total head loss. We already calculated the velocity from the given flow rate, and finally we can find the length here, which is inside of the friction loss. So it will be our answer. Okay, let's keep going with question 4, which is 2.12. And in this system, we have two reservoirs, which is point A and B, and they are connected with this pipeline with valves and with a pressure here. And the pipe length of the pipeline is 40 meters and diameter is 4 inch or 102 millimeters. And in this question, we need to find the minimum pressure, which is PO, that would keep the pressure head throughout the pipe positive. So we will find the pressure at this point. The pressure will be positive throughout this pipe. So the crucial part here is the most likely location for the negative pressure is the highest point in the system, in the pipeline, so that we can either choose 4 or 5. Since to consider more head losses, we can choose 0.5. So if we make this pressure as 0, so we can make sure that the pressure will be positive throughout the pipe. So let's say we need to satisfy that condition, which is pressure at 0.5 will be 0. So with this condition, we can start solving the question. So the main idea is ensuring that the pressure at this point is 0. We selected this point because it is the highest point in this pipeline. So it is most likely location for a negative pressure. So if we find this as 0, then we can make sure that the pressure will be positive throughout the pipe. So since we selected this point, we can write the energy equation between point A and point 5, so that we can generate our first equation to find velocity and pressure in the system. And first, energy equation for this reservoir. And it is equal to H5 P5 over gamma plus and head loss, of course. So we can eliminate something here, of course. First of all, since we want pressure at 0.5 as 0, this value will be 0, first of all. And unfortunately, we cannot eliminate pressure here because it is where we have pressure in the system. And we will not have anything to remove here. So we can keep going with the equation. And let me go with the head loss first of all. So in the system, as we know, we have two different head losses, which is friction head loss throughout the pipe and also minor loss. Let's say it HM. So for the HF, we will have friction factor L V square over 2 GD, and for the minor head loss, we will have sum of loss coefficient V square over 2G. And the elevation of reservoir A is 10 meters. And here the pressure at point A is PO, so I can directly write it. And actually the velocity will be 0 here because it's a large tank and we are considering the surface of this tank, so that it will be 0. This is equal to elevation at 0.5, which is here, and it will be 9.5 meters plus V5, or we can say it the velocity of the pipeline, because it will be same, plus the V square over 2G is common between these head losses, so I can write like this one. And from A to 5 we have some minor losses. So these are entrance to pipe, here's the valve, and I think that's all. So we will have 0.5 here and 12 here, and also head loss, the friction head loss will be FL over D. And in this question, we don't know the friction factor here because we still don't know the velocity here. So we can assume a friction factor, and with this friction factor we will get Reynolds numbers, we will get E over D, and finally we will get another velocity, so that we can compare each friction factor if we made the correct assumption. So let's assume that the friction factor is 0.02. So if we write this value here, it will be 0.02 times the length of pipe between A and 5. So it will be, we have 10 here. I think seven. Yes, we have 5 here, 15. We have 5, 20, and we have 7.5, 27.5 plus 5, it will be 32.5 over diameter. So we can write 0.1 or 2 meters for the diameter. And from here we can get this first equation. So PO over gamma will be equal 19.9 V square over 2G minus 0.5. So let's make this equation 1. Okay. Since we still don't know the velocity in the pipeline, we can write another equation between point A and point B, so that we can eliminate something, and we will get same PO over gamma equation, so that we can equalize each other, so we can get the velocity. So let me write that. Energy A to B PO over gamma plus the elevation 10, and we don't have velocity here, and for point B again we will eliminate velocity because it will be 0, and also the pressure will be 0 as well because it is open to atmosphere, so that we will have this elevation and head loss. Okay. So here we will have 2.5 if we move this value here, and here we need to write the head loss, total head loss. Again, we will have both fractional head losses and the minor head losses. So if we start with minor head loss, first of all, we will have this entrance to pipe, which is 0.5. We will have 12 here, and we will have another valve, which is 10. We will have the discharge or exit from the pipe, which is 1. And these are minor head losses. And also we have fractional head loss throughout the pipe, so it will be F, or we can directly write, because we assumed F as 0.02. And the length was 40 meters over 0.102, which is the diameter. Actually, let me write this. Head loss is equal in the parentheses of V square over 2G. And this will give us another equation. For PO over gamma, it will be equal to 31.3 V square over 3G minus 2.5. And let's write this is equation 2. And if we solve these equations simultaneously, let me remove that. So if we solve this equation 1 and equation 2 simultaneously, because we have the same PO over gamma and PO over gamma, and the only unknown is V square over 2G, so we can get velocity from here. So from equation 1 and 2, velocity is 1.86 meter per second. And now, since we know the velocity here, we can calculate the Reynolds numbers, and we can calculate E over D here. So we can get the actual friction factor using the Moody diagram. And let me write that, Moody. So the Reynolds number is dV over kinematic viscosity. And it gives 1.9 times 10 to the power of 5. And if we do E over D, it will give 0.00441. And using these values, we will get the friction factor. So the F will be equal to 0.01185. And I will continue with the clean screen, and we will continue from the friction factor here, and we will use that value in the actual equations here so that we can get new equations, equation 1 and equation 2. Let's keep going with this clean screen. So we calculated the friction factor from model diagram. So we had two main equations, which is energy equation from point A to 5 and also from A to B. The only difference between these equations and the previous equations, we just changed the friction factor here, because first we assumed that it was 0.02, and based on that we calculated the velocity, and from that velocity we calculated a new Reynolds number, and then we calculated the friction factor as 0.0185. So we just replaced the previous friction factor value with this new one, and from here we can get G minus 0.5, and from here minus 2.5. So again, based on these equations, both of them are equal to P over gamma. Based on these two equations, we can calculate the new velocity. And it gives velocity as 1.86 meter per second. So that we calculated the same one, and if you remember, we calculated this friction factor based on this velocity. So since it is still the same, we can say that the friction factor is okay. And since we calculated the velocity, we can use either equations, either this one or this one, so that we can get the PO value. Let me use this first equation. And this will give us 2 meters. But this is not the value of the pressure, this is value of the pressure head. So from there, PO is equal this is specific weight of water, and this is in meter, this is Newton over cubic meter, and this gives us 28.6 kilopascal. So this means that when we have a pressure of 28.6 kilopascal at this point, we will make sure that the pressure throughout the pipe is positive. So this is a theory reservoir question, and we need to find the flow rate within each pipe, pipe 1, pipe 2, and pipe 3. However, we don't know the flow direction. So, for example, in the first scenario, it can be the water can be coming from reservoir 1 and then it can split to reservoir 2 and 3, or water can be coming from both reservoir 1 and 2, and they are merging at this junction point, and they are flowing to pipe 3 and then reservoir 3. Since we don't know that, we need to start with some assumptions. And since we have this water surface 2 here, we can give some values based on this value, because we can assume this as the middle point. So based on these values, we will assign values, and then we will find the direction. So the main issue is we need to find the elevation of this junction point, Hj, and also the elevation of point J. So for example, we can start with, let's say, 5,165 feet, and we will start with this, and then we will see how it goes. Since we have this value, and the coefficient is given as 140, and it will not change based on the velocity. So if the elevation here, water surface at this junction point, is 1,165, then we will head loss of 35 feet. It is because the elevation, the water surface is 5,200 feet here, and we have 5,165 feet here, so we have 35 feet loss. And for the second pipe, we will have 5 feet, because it was 170, but we have 165. And for the last one, we will have the water surface is 5,100, but we have 165, so that it will be 65 feet. And as I give the equation here, we can find the slope based on the head loss over length. So for these values, we will get 0.00875. So basically it is 35 over 400 feet for this first pipe, and for the second pipe it will be 0.0025. Basically it's the same, and 5 over 200 feet, 2000 feet. And finally we will get 0.02. So these are slopes based on these head losses, based on this assumption. And let me write that. And also, if you continue with the hydraulic diameter, which is d over 4, and it will be 0.75, 1.25, and 1. And this is basically d over 4, 3 over 4, 5 over 4, and 1 over 4. 4 over 4, which is 1. And for the velocity, we are going to use this equation. So this is the coefficient. We have 140 here. We have hydraulic diameter as calculated here. And we have slopes, so that we can calculate velocity for each of these. we have 835. And now based on these velocities, we can calculate the flow rate, and flow rate was V times area. If I directly write the value of discharge or flow rate, we will get 84.34, 163.9, and 292.6. So we will have two different scenarios, as I mentioned. So the first one can be Q1 is equal Q2 plus Q3. This is the case where water is coming from reservoir 1 and then it is splitting. Or we can have Q1 plus Q2 equal to Q3. In that case, we have water coming from here and water here, then they are merging here, and then the water is going to reservoir 3. And this occurs based on a condition if the elevation of this water surface at junction is lower than water surface at 2. Sorry, it will be opposite. So for this case, the water surface of junction is higher than water surface 2. This means that we will have water going from this point to this point. So the shape can mislead, but when Hj is higher than water surface 2, so it will be something like that. Then water will be moving to reservoir 2. But in other case, in the case where water surface 2 is higher than Hj, this time this elevation will be lower than this one, and water will be going from water surface 2 to Hj. So we will try both of these scenarios to get the final flow rate. So the first one will give, so we have Q1 here, Q2, Q3, and when we do that, it is going to give, just a second. Okay, in the first case, we will get something like minus 372 for this one, and for the second one, we will get minus 44. So the purpose is making a value which is very close to 0 for the sum of discharge, for the sum of flow rate. So when we find something like 0 or 1, then we can stop. So for this question, we assume that the Hj is 1165, but it gave a minus value, a minus 44 and minus 372. So that we need, this means that we need to decrease our Hj. So for example, let me use the green. And if we assume that Hj as this value, which is the actually solution. So I directly use that, and this is assumption 2. And when we use this value, we will calculate everything from the beginning, so that we will have loss of 37.2, which is here. Head loss 2 will be 7.2, and head loss 3 will be 62.8. And for the slope, again, we have 0.093, 0.036, and 0.02093. We have same values here because this value is based is changing based on the diameter, and based on these values we can calculate the new velocity, and it will be these values. And again, using the continuity equation here, we can get final flow rates. And let me do the calculation here. And for the first scenario, we will get, it is a scenario of this one, where Hj is higher than water surface 2. And it is giving minus 400.2. And for the second scenario, we will get minus 0.6. So this is actually what we want from this equation, because when we sum all of these flow rates, we are getting a very small value, which is very close to 0, which is minus 0.6. So we can accept this assumption here, and the final Hj will be 1162.8 feet. And for example, if we had less value from that, for example minus 20, we were going to decrease this value again. But for example, in the case where the final final flow rate, for example, let's say positive 40 feet of 40 cubic feet per second, then we were going to increase our Hj, so that we can decrease the final flow rate.
Okay, now we are at question 6, PowerPoint 3.6. Here again, we have a three-reservoir system, and we need to determine the surface elevation of the reservoir, given the following: water surface elevation and pipe data. So the highest reservoir is inaccessible after a mountain storm. So we are going to find the surface elevation of this reservoir. And we have these values here. All of the pipes are rough concrete with a roughness of 0.6 millimeters. So we are assuming a complete turbulence. And the actual elevation of junction is 2049. And the pressure at the junction is 97.9 kilopascal. So in the previous question, we didn't have the elevation of the junction, which is here. And we didn't know the pressure at this junction as well. But this time, since we know the elevation of junction, we can define the direction of flow. So the velocity, the water surface at reservoir 2 is 2090, and here it is 2020, and here we don't know. But for now, we don't need to know to define the direction because it is the highest one, and we are going to find that. And we have junction here, 2049. So here we can say that the water will be moving from reservoir 1 to the junction, and also from 2 to junction, and they are merging at this point, and then it moves to reservoir 3. So basically we have Q1 plus Q2 equal to Q3. And now we are going to write energy equations between all of these points. Let me take that. Okay, first let's get started with energy equation between J and 2. So I'm gonna write it here. So we will have H2 plus square root 3G plus T2 over gamma equal to Hj plus Bj over gamma plus, of course, head loss. And here we will not have velocity at the surface, so it is 0, and also the pressure is 0. And also we don't have velocity at the surface because it is large. It's like large tank and there's no movement. However, we have a pressure head, and we can calculate it as it is given as a 97.9 kilopascal, and it means it is 97,100 pascal over gamma, and gamma is specific weight, and it was 1,790 Newton over cubic meter. And this is going to give us 10 meters plus head loss, and the Hj, which is the elevation of the junction, is 2.49. So actually, this will be the same for all of these energy equations. So we can write it like this one. So if you continue with the energy equation between 2 and J, 2090 is equal to 2059 plus head loss. And the head loss here is F and V square over 2GD. And it is F times length of 2 times the velocity over 2.981 times 0.3 meters of diameter. Here again, and we don't know the friction factor, so that we need to assume a value. And this time we are going to assume it based on E over D. E over D is 0.0015. And since we have a complete turbulence, we can assume a value of 0.022. And actually, I can show it here. So here we have E over D, which is 0.0015. So it will be around here. And since we assume that it is complete turbulence, we are going to follow this curve. And it gives almost 0.022. And we will directly use that friction factor. Here we say, and we assume that because we don't have Reynolds numbers, and we assume that it is complete turbulence. So it is around 0.05, and we assume that it is 0.022. And if we write this in this equation, we can get V2 as 3.04 meters per second. And this is the first velocity we found, and it is in the pipe 2. And from there, we can calculate the flow rate, which is V2, A2. Okay, so we calculate the first flow rate. And now we can follow the same process for reservoir 3 and HJ. So this time we are writing this energy equation between these 2 points. And since we are going from J to 3, I will first write the J. And we already calculated energy level at J as 2059. So I will directly write that. And this will be equal to H3, pressure head, velocity head, and the head loss. Because as I mentioned, this time we are going from junction to reservoir 3. So there will be head loss throughout this pipe. So we wrote the J first and the 3 as a second term here. And this is same for all of these pipes because we calculated energy level as 2059. And similarly, we can calculate head loss. And it will be F times times acceleration times the diameter. And here E over D is 0.002. And since we are assuming a complete turbulence, we can estimate friction factor is 0.021. And if we write this friction factor in this equation, and since we have a value here, we can calculate velocity at 3, and it will be 2.76 cubic meter per second. And then we can get the flow rate. And now we calculated the most important two terms, which is Q2 and Q3. These are important because, as I wrote at the beginning, Q plus 1 Q2 is equal to Q3. So from here, we can calculate the flow rate at 0.1, which is here. So let me write that again. And Q2 was 0.382, and this one is 0.542. And from here, Q1 is 0.16 cubic meter per second. And finally, we can write the energy equation between 1 and J. Again, we are going from 1 to J because the water surface is here the highest, and we have a lower elevation here, so that the water will be moving from 1 to J. So on the right hand side, we have terms for J, and on the left hand side, we will have terms for 0.1. So it will be H1, velocity hat, pressure hat. And again, it is going to be same. And this is energy level at J. And here we have zero velocity at the surface, and we have zero pressure. And also I forgot to mention that we will have head loss because we are going from 1 to J. So the elevation here will be equal to 2059 plus head loss. And for the head loss, we are going to write F times the length of pipe 1 and the diameter is 0.3. Here I can directly write velocity as V, because the velocity at the surface is 0, but we are going to find the velocity at this pipe. And similar to previous reservoirs, we have E over D as 0.002, and assuming a complete turbulence, the friction factor will be 0.0235. And this time, we actually know the velocity at the pipe 1 because we know the Q. So let me write it as V1 again. And from here, V1 is equal to 2.26 meter per second. And don't mix up this velocity with the velocity at the surface. This is of course 0, but this velocity is for this pipe. And since this time we know the velocity here, we can calculate the H1. H1 is 2097.7 meters. So let me summarize the question again. So in this question, as a difference from the previous one, we know the elevation of the junction so that we can determine the direction of flow at the beginning. So we said that since this point is lower than water surface 2, water is moving from reservoir 2 to this junction, and also from reservoir 1 to junction again. And they are merging here, and the combination of these flow rates is going to here. So this gives us this equation as Q1 plus Q2 is equal to Q3. And we also wrote energy equations between all of these points. So between reservoir 2 and J, 1 and J, and 2 and J. So we started with 2. And energy level at J is same for all of these equations because we have elevation of junction as 2049. And the pressure head is calculated as 10 meters because the pressure was given. And so since we are going from point 2 to J, we have head loss on the right-hand side. And then we had the elevation of water surface 2, which is 2090. And the only unknown was head loss and actually the friction factor and velocity. Since we don't know the velocity here, we are not able to calculate the Reynolds number. So that we actually assumed a friction factor because in the question, it is mentioned that we have complete turbulence. So based on E over D and based on the complete turbulence, like this curve, we assumed friction factors for each of these pipes. And since we can replace this value here, we were able to calculate the velocity. Then from velocity, we calculated the flow rate at point 2. As similar to this process, we applied the same one from J to 3. This time it is from J to 3 because water is moving from J to 3. And head loss on the right-hand side. The energy level at J is still same, 2059. And similarly, we didn't know F and V. And based on the E over D, we assumed friction factor is 0.021. And from that, we calculated velocity and discharge or flow rate. And as I mentioned at the beginning, we had this equation, which is Q1 plus Q2 is equal to Q3. So based on that, we were able to calculate the flow rate in pipe 1. And again, we wrote the energy equation between 1 and J here. And here, we removed these values because it is open to atmosphere and it is very large tank. So only unknown is H1 on the left-hand side, and other unknowns are friction factor here. So again, we assumed a friction factor based on E over D. And this time, we actually knew that we have velocity because we already know the flow rate in this pipe. From flow rate, we calculated the velocity as 2.26. And since we have every value here, we calculate the elevation of the highest point here.